So calculating unequal slope hip roof components. Okay, so this is our second in-class example. I just decided to do a video with it to make sure that we're comfortable with that. We can kind of pause it, replay, that kind of a thing. One of the first things that we're going to have to do is do the drawing. Okay, so we're told that the side slope, so the side slope of the roof, this is going to be the side of the roof here. This is what we're going to call the end of the roof over here. Okay, so you can see end slope will be here, side slope will be here. Once we get the drawing done, the trapezoid will be like the side, and there's a triangle that'll form here. That triangle will be the end. So in this case here, we're given the side slope. We're not given the end slope, so end slope to be determined, but they also gave us the ridge. Okay, so that's going to help us get the end run, which then will also help us get the end slope. So one thing with a unequal pitch roof, right now we're looking at 18 by 28 feet. That's not actually the building size, that's the roof size, right? So the roof is actually 28 feet long and 18 feet wide. So we're going to call this the span, but really it's not really the span, right? It's the span of the roof, not the span of the building. The building is actually a little bit smaller. So if we look at our projection is 24 inches. So in reality, if we took 2 feet off of here and 2 feet off of here, the building is actually 14 feet. And then, so maybe I'll just write that down. So 14 feet by 28 feet. Again, we have 2 feet here, 2 feet there. So we take off 4 feet off of 28, gives us 24 feet. So the building is actually 14 by 24, but the roof is 18 by 28. So, like we discussed in class, we've got to make sure that with unequal pitch roofs, we do our calculations to the fascia board because there's a difference in slope. So one slope is going to drop more than the other. So we want to make sure that we line up our fascia boards. Okay. So I could maybe spend a couple seconds on that, but maybe I'll wait till we find the slope to go over that. Okay. So let's start off by doing what we can on this drawing, right? So I'd like us to kind of start with the drawing if possible. So we're given a ridge. So the ridge is 20 feet. The length of the building is 28 feet, right? So there's a difference there of 8 feet. So if I want to find the end run, and in this case here, what I could actually do is use that information. So the end run is how much feet of run do I have on the end of the building, okay? So in this case, if I took the roof length and then subtracted the ridge, and then take that and then divide it by 2, right? So if I'm given the ridge, so if given ridge, this is kind of what we should do, okay? So the roof length is 28 feet minus the ridge, which is 20 feet, and then we divide that by 2. So we're going to end up with 8 feet there, divided by 2 equals 4 feet. So that means we have 4 feet of end run, okay? So that would be my starting point to actually lay out, right? This is the corner of my building. That's 1 foot, 2 foot, 3 foot, 4 foot, okay? How do I know that every box is a foot? I just basically counted this out before we started here, but there's 18 feet, therefore there should be 18 boxes there, which there is. Sometimes it's going to be a box is equal to 2 feet, so you just got to make sure you pay attention to that. And then we'll go with that. So 4 feet of end run, therefore I go 4 feet here, basically. And I draw that line across. Okay, so that's going to locate where the hips go. So unequal pitch, hips no longer run on 45 degrees. Okay, so there's my line there. 4 feet over. Should also locate the center, this direction, right? So I have 18 feet, so if I divide that by 2, I got 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the middle right there. Okay. I'll go ahead and draw that across. Okay. Now if I went from this point to that point, that's my hip. And notice that the hip doesn't hit the corner of the building. Okay, so the hip doesn't hit the corner of that building, which is normal, right? When we do an equal pitch roof, the hip hits exactly at the corner because it's a 45, right? Now we're not on 45, so we're actually missing the corner by quite a bit, which is called the hip rafter offset. So how far is the hip rafter located from the corner of the building, right? So something new there, right? Because we're running on an angle. Go ahead and draw that in. Do the same in all corners there. Okay. From there, I can look at my instructions. It tells me rafters are 24-inch on center. So from there, I can lay out my rafters. So just like any other roof, we work off of the common. That's a common, and a common. We do our layout off of our common to be 2 feet on center. So if I go from there, I'm going to go 2 feet on center all the way to the other end of the building. So I'm actually going to draw this one in here complete. It's not going to take me too long. I'm drawing in all my common rafters, which are on the side slope. Okay. And one more. So it ends up working out that I end up with exactly 2 feet at the end. That doesn't always happen. Because it's an interval of 2 feet, it will work out. If that was an odd number, that wouldn't. So it's not the end of the world, right? Start from one end, work one direction. Once we get into the corners, work off those commons again. Go 2 feet on center this direction, and then go 2 feet on center that direction. So the plywood might get required to be cut here, but that's okay, right? So we want to make the math for those components easy. Might waste a little bit of plywood, but that's okay. So I have a hip jack there, I have a hip jack there. So I stop when it hits the hip, stop when it hits the hip. Come over here, do the same thing. So 2 feet on center. And then I'm going to do the same on the, so that's the trapezoid, which we call the side slope. So this section here is going to have a slope of a 12. On the end here, we don't know yet. We have to determine that, okay? But on the end here, I'm going to do the same thing. I'm going to work from the common rafter, and I'm going to go 2 feet on center. Then another 2 feet on center. Then another 2 feet. So I'm going to go ahead, I'm going to draw those in on both sides at the same time. I'm going to draw here till it hits the hip, stop. Draw here till it hits the hip, go over 2 feet. Follow my graph paper there. So there and there. And then one more time there. The last one I don't think I'm even going to bother. It's going to be small enough that it wouldn't be necessary to actually cut it. Right? It would be too small. You can see even this one here is not even going to have a bird's mouth. Right? If it had a bird's mouth, it would have to be that one or that one. I'm still going to put that one in, but I'm not going to bother with the one that goes here. So we'll do the same on the far side here. Draw that in. We're just about done there, ready to start filling in our chart there. Okay, so that's good. So let's grab the homework sheet there. Now this is so we do the drawing, but then we do the math to correspond with it. So I want to label it, right? It says down here, label all rafters. We want to label those rafters according to the math that we're doing. Okay, so let's try and get these somewhat on the page here. Okay, so first thing we're going to do is look at the top here. So it says side roof, that's the side roof. Trapezoid, that's the trapezoid. Okay, the slope was given to us was an 812, so you can write that down. 812 there. Total span, fascia to fascia. So basically it's the span of the roof there that we're looking for. This would be the span. So the total span there is 18 feet. So total run would be half of that. So what is the run of that rafter? It would be 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, or span divided by 2, 9 feet. Okay. Something that we actually have to figure out now is the total rise. So everything kind of works off of the total rise. We're actually going to use the total rise to determine this slope here. Right? So there's an angle here coming through, but we're going to use the total rise there to then determine the slope on that end. So the total rise, same as usual, right? We take the run, in this case the run of the roof, multiplied by the unit rise. We can see that, yeah? So the run is 9 triangles. That's how I like to call it, right? It's 9 feet, so you got to make sure that the run is in feet, then that turns into triangles or parts, and then the unit rise is 8. So 9 times 8 is 72 inches, which is basically 6 feet. Okay? So that's going to be the rise of the roof. on both sides, right? So this 812 side is going to rise to 6 feet. This end run, which we don't know yet, and the end slope will also rise 72 inches there. Okay, so we can go ahead there now. We'll kind of forget about the end until we get there, right? So this first little section here is to do basically with all the trapezoid. So we're going to kind of fill that in. The first thing that we want to label is A. So we're going to put A right at the ridge. We were given the ridge, right? So that was given, it was 20 feet. We could count that out as well, though, right? Every box is a foot, so that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So our drawing is done correctly. If we're given the slope, it would be a different story. We have to try to determine the end run. So sometimes you're given the slope. Then you actually got to use this formula here, right? No, I guess not. It wouldn't be that formula there. But if you're given the slope, you kind of got to backtrack. You'd be given the unit rise. So we kind of look at that formula. But if we had total rise, our initial formula is run times unit rise. So if we were given the slope, we would know this, we wouldn't know this, and we'd also know the total rise. So if we were given the slope, we'd want to alter that formula to determine what we're missing. We're missing the run, right? So we would take the total rise, which we just figured out, which we'd always be able to figure out. Because we're taking that over onto this side of the equation, we have to make that multiplication into a division, the opposite, and that would be divided by the unit rise. Okay? So some cases, when we're not given the ridge, or not given the end run, we're given the slope, we have to find the run by taking the total rise and dividing it by the unit rise of the end slope. Unit rise of the end slope. So not the 8, but whatever is here. So we don't know that right now. Maybe we could try that once we know the slope, because there's two different scenarios. Sometimes you're given the slope, sometimes you're given the ridge, or the end run. So knowing the ridge and knowing the end run is basically the same thing. Right? So if you know the ridge, you basically subtract 20 feet off of the roof length. That'll give you what's left over. We need half of that on either end, so we divide it by 2. If you're given the end run, that means you would know that this is 4 feet, you would know that that's 4 feet. So basically your end runs are occupying 8 feet. So that means that there's 20 feet left in the middle, which would be your ridge length. So either way, you're kind of getting the same answer there. Okay? So let's kind of keep on going here. So the total length is 20 feet. I'll write down my final answers over here. That's just room for work. B now. B, I think I'm going to label it right here. So that's B right here. This is also B. Those are all B's, right? All the way through here. Same as on the other side. So the way we're going to calculate B is just like any common rafter that we've done before. Again, we're calculating the common rafters now, not the line lengths. Line lengths go from the center of the ridge to the outside of the wall. We're now going from the center of the ridge to the outside of the fascia, so the fascias line up all the way around the building. Okay, unequal pitch. We have to include the projection in our calculations. So now we're taking the run of the roof. So run of the roof multiplied by the UCR. So the run of the roof is going to be half of the span. So basically 9, right? We have it right here. 9 feet, so therefore 9 triangles. Multiplied by the UCR of an 812, which is 14.42. It's on the frame and square. Right? Under the, we should be familiar with that right now. So 812, line 1 is 14.42, so that's a chart that I gave you, but I also have the frame and square on the back side of that, so line 1 under the 8 is 14.42. Okay, so both those numbers will be found on that sheet. So now I just have to pull out the calculator and then do the calculations for that. Okay. So if I go 9 times 14.42, I end up with 129.78. That's inches, so 129. I'll subtract that, left with fraction of an inch, I'll multiply that by 16. So that gives me 12/16, which is 3/4. So that's basically 10 foot, 9 3/4 is the length of that rafter. Okay? This is kind of where I'd like to throw in a sketch here. Okay? So So kind of what do we have so far? I'm going to hide this map for a second here. Do a quick little sketch of this corner, but in 3D. So this line here is the first line I'm going to draw, and then I'm going to draw this line second. So kind of the horizontal plane of that roof. That's approximately the middle. Just a sketch here so we kind of understand what's happening. We're going to come over 4 feet there because we have 4 feet of end run. So that'll go right across. So that's a horizontal plane right there. Just kind of look at what we've done so far. If I made a 90 degree here, that would be my total rise. So total rise was 72 inches. It brought us to that point right there. So that's going to put a little mark there saying that that's 72. If I actually connect that to the corner here, that's what we just calculated, which was B, our common rafter. What was the length of that? It was 129 3/4. So 129, I'm going to put the actual decimals there. 129.78 is what we had. Okay. Now if I actually connect this to here, that's going to be our hip. Right, so if I connect that all the way to the corner there, that's our hip. Okay. So that's our common rafter. That there is our hip rafter. So basically what we need to calculate next is C. C is our hip jack rafter number 1. Right? So hip jack rafter number 1 is going to be right here. So that was B. That's C. Right? So that's B here. I'm missing C. C is 2 feet over. So if we come 2 feet over, basically that's going to be in the middle. And if I connect that to where it hits the hip, that's now the length, right? So that's the length of the common rafter for B. This is going to be the length of the common rafter for C. That's 2 feet on center because we're told our rafters are 2 feet on center. So now what I'm going to do is use similar triangles to solve for C. So we know this distance. So that's a big triangle there that we can see, right? So that's 129.78. That's 4 feet. There's our hypotenuse. Then we have a smaller triangle where we don't know this distance. We know this one though, because if that's 4 feet and that's 2 feet, that means we have 2 feet left over here. If we know the base of that, we don't know that. Well, that's a perfect opportunity to use similar triangles, okay, to get the length. Comparing this big triangle to this little triangle to determine the length of C, okay? So I'm going to just maybe push that up to the top for a second, kind of draw those triangles. I want to draw that big triangle. Can we still see that? Looks a little fuzzy to me, but so you can see that big triangle there. So I'm going to draw that one right here off to the side. I'm going to try and label it as best I can here. So that's 129.78. And at the bottom here, it's 4 feet. But since that's in inches, I'm going to keep this in inches as well. I have to. So that's going to be 48. So it's 129.78 on this side, 48 inches across this side. Then I have a smaller little triangle there, which this is C, and then that's 2 feet. So I'm going to put that as 24 inches. Keep everything in inches here. It's really important to keep those in inches. This could be in feet, which would mean my answer would be in feet. But just for simplicity, I'm just going to make sure that everything's all in inches. Well, so now I have two triangles that are similar. That's basically a fraction, and that's a fraction. So now I'm going to write it down as a fraction. So 129.78 over 48. So the 129.78 is equal to C. Equal to C. The 48 is equal to the 24. Okay. And then from there, I can basically just cross multiply. This is half, so that number there is going to be, this is going to be half of that as well. So that's a similarity I can see pretty quickly. But we're going to cross multiply, do it the long way as though I'm not seeing any little tricks there. So I'm going that times that times that, right? That's kind of how we do our similar triangles. So I'm going to end up with basically 48C, that's my inch symbol, is equal to 129.78 times 24. Then what I got to do is I got to get C by itself, so I have to divide by 48. So whatever I do to the left side, I have to do the same to the right. And then I'm going to get my answer. So I'm going to write my answer down here in this corner. Okay, but so we can speed this up. We don't have to write this. We don't have to write this. we could just go that times that divided by that. So I really only need to write that down the line eventually. But just as first few examples of kind of playing around with similar triangles, I just took that triangle, made like two fractions out of it that are equal to each other, and then from there solve by process of elimination and canceling out. So that cancels each other out, right? And then plug in the numbers, and then away we go. So 129.78 times 24 divided by 48 gives me 64.89. So I might just write that 64 here. Now I'm going to subtract 64 out of the calculator, multiply that by 16, so that gives me 7/8 there. Or I could also write down that that's 5'4" and 7/8. So maybe both answers there are not a bad idea. Okay. So if I was at 64.89 and I wanted to go to that, just a little refresher there, 64.89 is my answer in inches. If I divide that by 12, there's 5 feet. So I write 5 feet down, then I subtract 5 feet out of the calculator. Now I have decimal feet, so I want to put that into inches, so I multiply by 12. That gives me 4 whole inches, so I write that down. Now I subtract that out of my calculator. I'm left with all my fractions of an inch there, so I want to know what that is over 16, so I multiply by 16. There's my numerator. So if that 2 was 5 or higher, I'd have to make that 15/16, but it's not, so now it's 14/16, which gets reduced down to 7/8. Okay? So now that we have that, that's basically done, right? We don't have a D not available, and we don't have an E. If we did, what I would do is find a common difference for those rafters, so I could then just subtract off of the length. Okay, rather than do all this math, I would find a common difference. We're going to have to do that on the end run there, so I'm not going to bother talking about that right now. Okay, so I'll just push this aside for now. So where are we now? We're basically, so that's not available, that's not available. Okay, end roof triangles, that's the end roof triangle there that we're talking about. First rafter we need there is F, but before we do that we need the slope. We don't know the slope, right? So this is kind of a little bit of information here to kind of help you with that. So the end run is 4 feet. We predetermined that, which means there's 4 runs, which means there's also 4 rises. Okay, so that's kind of a little bit of a hint there on how you can, how we can actually figure that out. Okay, but here's a formula. So if we want to get the unit rise, we take the total rise and we divide by the number of rises. Okay, so the total rise is basically 72. Right, we have it right there, 72, divided by the number of rises, which is 4. So 72 divided by 4 is going to give us our, so you can write that down here, 72 divided by 4. So 72 divided by 4 gives us 18. So that means it's 18, which is an 1812 roof. Okay, so that's one way of manipulating the formula. Another way to do that is to kind of look at similar triangles again. Right? So if we kind of look at, basically it's this triangle right here. That triangle right there. That's 72, that's 48, right? So if I redraw that triangle, that's a 90-degree corner there. So if I redraw that triangle just over here, and I'll write down those numbers, that's 72 inches. That's 48 inches. So my drawing's not very accurate. That should be much higher than this, but we're trying to determine slopes. This is another way, a visual. I find this is a little bit easier on the brain when you have a lot of information in your head. We're trying to solve what is the unit rise. So you see the triangles, how they pop up, right? That triangle is going to be similar to the slope of the roof. We're missing x. So we're just basically cross multiplying it. So 72 over 48. 72 is equal to x, 48 is equal to 12. And then from there, just cross multiply, like we just did. Okay, so that times that divided by that. So I'm not going to bother writing out the long way there. So if I go 12 times 72, and then divide by 48, we end up with 18 inches there. a little bit quicker, I think, and visual. That triangle is the same as that triangle, so a little bit quicker way of coming up with that information. Either way gives us the same answer. Okay? So now we know the slope on the end of this building is a 1812, fairly high, right? Fairly high pitch, but that's somewhat common with unequal pitch roofs. That's kind of what they're looking for. So if we keep on rolling here, there's F. Now we know the slope, so that's a common rafter, right? Common rafter on the end roof. So we're going to take the run, and multiply by UCR. So run of the roof, which is the end run, is 4 feet. 1, 2, 3, 4. So 4 triangles multiplied by the UCR of an 1812. So I don't know that one offhand there, but we'll just take a look here. 1812, line 1, 21.63. Right, so 21.63 is the inches, is the unit length of that slope. So if we have the triangle there, what does that mean? That means this is 12, this is 18, and that there is 21.63. Right, so that's why there's basically 4 triangles there. Each triangle has a length of 21.63, so that's why we're going 4 times 21.63. Okay, so we keep on rolling with that. We'll go 4 times 21.63. We end up with 86.52 inches, which is equal to 86 and half, basically 86 and a half. So it's 86 and a half here, or 7 feet is 84, so we have 2 inches left over. So 7 foot 2 and a half. Okay, so I just like to do both answers there, just out of habit. G is next, so we're going to tackle G the same way as we tackled C. We're going to look at that 3D drawing, okay? With equal pitch, we can sometimes count, but we can see we're not actually hitting that dot right on there. So I can't, that's not 3 feet, that's 3 something. Okay, so we can't go by 3 times UCR. Here we could, because it was an even number and we knew it was, but here I can't. I don't know the run, right? So I can't guess at it. I'd have to calculate the run. So that's one thing I could do, right? I could use this big triangle, which I know this distance, and I know this distance, against the smaller triangle, which is this one right here, which I know this distance. It's 9 feet to here. That's 2 feet on center. That means it's 7 feet to here. So I know that's 7. I don't know what that is. So I could determine that, and then that would give me the run of that rafter. And then I could take the run of the rafter multiplied by UCR, and that would give me the length of that rafter. Okay, but I want to do it the same way as we just did looking off of this drawing here. So I'm kind of going to, right, we have F. That's F right there. If we came over 2 feet, that would give us our rafter, which is G. So that's G right there. So again, what do we know? We know that this distance here is 9 feet. We know that our on-center spacing is 2 feet. So that means we're coming back to this location. So from here to here would be 9 minus 2, which is 7 feet. So the distance from here to here is 7. Right? So I have 2 triangles. One where this is 9, and that is F. F we just determined the length, which was 86 point, was it 5.2? Yeah, 5.2. So we know that distance, right? So we know that that's 9 feet or 108. I'm going to use the inches, right? So 108 and 86.52. The other triangle we're trying to look at, we know that that's 7 feet or 84 inches. But we don't know G, which is the length of the hipjack rafter, number 1, which is what we want. So that's what we're going to compare. We're going to put both of those triangles down on paper there now. So the first triangle we have 108 here. And here we have 86.52. We're comparing that to a smaller triangle where this is 84. And that's basically G. Okay? So we're just going to cross multiply again. I'm not going to bother writing it all out. I'm just going to go with that times that divided by that. Okay? So cross multiply, that's basically like a fraction there, and that's a fraction there. I cross multiply. Then I have to divide by that at the end, right? So it's kind of a pattern there that we got to kind of memorize. So 84 times the 86.52 gives me that. Divide that by 108. That gives me G. So G is 67.293. just lose everything. So 293, so that's equal to 67. So I'm going to minus the 67 there. Multiply that by 16 to find the numerator, which gives me 5/16. So that's going to be 67 and 5/16, or 5 foot 7 and 5/16. Okay. Now we can do the common difference here. Okay, so I have several other hip jack rafters. So we've got the length of that one, we've got the length of that one. We still need H and then I to complete that, right? So now what I can actually do is find the common difference. So for looking at this, I now know that G is equal to 67.293. And I know F is equal to 86.52. So to find the common difference for the 1812 side, I'm going to take common rafter minus hip jack rafter number 1 on that side. So the common rafter is 86.52 and hip jack rafter is 67.29, I think it's 5 or no, 93. And that's going to give me the common difference. So basically, right, we have this length. We're going to subtract this length off of that length. So what that basically does is it gives us this distance, which is the common difference. It's basically how much do I remove off of the first rafter to get the second rafter. And that would be the same, how much do I remove off the second rafter to get the third rafter. Common difference, so it's the angle, right? It's on an angle there, not a horizontal distance. So if I take the common rafter length minus the hip jack rafter length, I've got a common difference, okay, for the 1812 side. It's only going to work on that side. We use common difference with equal pitch roofs, and that was on the framing square. No longer can we use the framing square to get that information. The only thing we can use on the framing square right now is UCR to calculate the common rafters for those rafters, okay? So in this case here, I'm going to go 86.52 minus 67.293. That gives me 19.2, let's say 3, okay? That's our common difference right there. So I might write that at the top of my sheet. Like in this corner here, I might just say common difference for 1812 is equal to 19.23. So I have it close by, okay? So now I can kind of continue with that, right? So basically now we're coming over 2 feet here and throwing in another rafter right here, which is H. So if I have the length of G, which is 67.295, and I subtract the common difference, which is 19.23 from it, that'll give me the length of H. Okay, so that's exactly what I'm going to do. So I'm going to take the length of hip jack rafter, number 1, minus the common difference that we just calculated. So hip jack rafter number 1 is 67.293. We're going to take off 19.23. That's going to give us our length. Okay. So I'm going to go 67.293 minus 19.23. That gives me 48.063. So 48 and probably a 16th there. Let's just double check there. Minus 48 times 16. Yeah, 1/16. So 48 and 1/16 here, and which is basically 4 foot 0 and 1/16. Okay. Hip jack rafter number 3. We're going to continue in that same pattern. We're just going to take the hip jack rafter number 2 and remove the common difference. So 48.063 minus the 19.23. That's going to give us hip jack rafter number 3. Okay, so 48.063 minus 19.23 gives me 28.833 inches, so 28 and 13/16. So 28 and 13/16 of an inch, or 2 foot 4 and 13/16. So we're pretty well going to stop right there. Right, that brings us to to the piece where it's almost getting too small there. So F, G, H, I. So J I'm not even going to bother with. Not available. Kind of too small there. Okay, so I'm not going to bother with it. Now that's pretty much done there, right? So hopefully that's kind of making sense. I think this drawing here, hopefully you could see it. It'll help us to get a lot of that math. So now we get to the hip rafter. So the hip rafter is basically this piece right here. That line right there. K. Okay? So there's a couple different ways we could actually get the answer for that. We have, three ways. We have this big triangle here where we know this distance. We know this distance. That's what we want. There's also this triangle where we know this distance. We know that distance. That's what we want. So that's Pythagorean theorem, right? We're trying to solve for the hypotenuse. And there's also another triangle in here. If we connected it from here to here, that would be the base of that triangle. This is the 90 degrees. So the run of the hip with the total rise of the hip, use Pythagorean theorem to then get the hypotenuse. So we don't know the run right here, right now. We could figure it out. We know the rise. So it would be one extra step. So I would prefer just to use this triangle right here, which we know this. We know this. We want to solve for that. So Pythagorean theorem with that triangle. So I'm going to write that triangle down right here. So instead of writing down 4 feet, I'm going to write down 48 inches. Keep it into inches. B is 129.78. And what I'm trying to figure out is the hip rafter. So I'm going to use Pythagorean theorem, square root of both of those numbers. So 129.78 to the exponent of 2 plus 48 to the exponent of 2. So if that's inches, make sure that's inches. And then we'll square root that. Okay, so I'm going to enter in the calculator just like I see it. So square root button, square root button, brackets, 129.78 x squared plus 48 x squared, close the brackets, press equals. I end up with 138 there, 0.372, okay, which is 138 and what? So that's a perfect example, right? That's 5 or higher, so I gotta make that a 6, so 6/16, which is 3/8, okay? So 138 and 3/8. So basically 11 feet is 132, so there's 6 inches left over. So 11 foot 6 and 3/8. Okay. And that's our length. Okay, we have that length there for that hip rafter. So that's pretty well taken care of. L is the hip rafter offset. So we talked about that a little bit at the beginning. Right? So we talked about that. The distance from here to here, that's L. Or it's the same as the distance from here to here. That's L. Okay? So we first have to determine this big triangle, a little bit bigger. We know that's 2 feet. We don't know that. Once we find that, we also know that this is 2 feet. So if we know the length of this side minus 2 feet, that'll give us L. So how do we find the length of this side? Well, we can compare it to this triangle here. So this is all plan view, horizontal. So we're going to look at these triangles now as horizontals. Before we were looking at them on an angle. So we know that the distance from here to here is 48. We know the distance from here to here is half of 18, so 9 feet, so 108. That's going to be our first triangle. So I'm going to put that down here. That we have our first big triangle there, where this is 48, this is 108, which is 9 feet. That's the big triangle. We're going to compare that to this little triangle. We want to know this side here, so we can subtract 24 from it. So we know that that's 2 feet across the bottom there. Again, similarities here, right? That's half, so therefore that would be half. So it should be 54 here, right? But we're going to do the math because we're trying to solve for x. That's a fraction, that's a fraction. So maybe I'll just do this one long there again, just so we could see that. So inches, we have x over 24. So the key there is apples to apples, right? Vertical with vertical, vertical with vertical, horizontal with horizontal, horizontal with horizontal. If you mix those up, you're going to get that wrong. Now we're going to cross multiply and then solve. So that times that divided by that, okay? So 108 times 24 divided by 48 gives us 54 inches. So x is equal to 54 inches, which is half of that, right? This is half of that. This has to be half of that to maintain that ratio. So we did the math. We didn't really need to, but now we know x. What is x? X is the distance from here to here. Right? So now what we have to do is remove 2 feet off of it, and then we'll have L. Right? So to get L, we take basically x minus the projection. So x is 54 minus the projection, which is 24, and that gives us 30 inches exactly. Okay? Which is 2'6". So if we measured from the corner of that building, 30 inches, that would be the center of that hip rafter. So from there we'd have to mark the angle, then from there go over half the thickness of the hip, draw a line, put an X on this side, and that's where I get nailed down. Okay? So we need to know that to be able to build. Okay? Last thing we need there is the amount to raise the wall. Okay, so amount to raise the wall. So the way I like to look at that is look at the projection. So our projection is horizontal. Right? So if we come out horizontal, our projection, we're told, is 2 feet. Right? It's on the plan, 2 feet. So I have to look at the projection in 2 scenarios there, 2 slopes. We have the side slope. So side slope is a 812, and then the end slope is an 1812, but still 2 feet. So what's happening there, we're traveling horizontally 2 feet, but on the side slope, we're dropping 8 inches every time. So if I come over 12 inches, I then drop 8. I come over another 12, I drop another 8. So we have 2 triangles that are being formed there that are 8, 12. We have 12 here, 8 here, 12 here, 8 here. So that's how much the projection is dropping on the 812 side. 8 plus 8, 16. On the 1812 side, same thing's happening, but now it's dropping more. So now that's 12, 18 is going to be longer. And we go over 12, and then another 18. So that's 12 here, that's 18 here. That's 12 here, that's 18 here. So now we could see that on a 2-foot projection, the 1812 side is dropping 18 plus 18, which is 36. Okay? So now we have a difference in projection between the two. Right? So we have a basically 36 minus 16 equals a 20-inch difference. So we have to make sure that the fascia boards line up. Right? So if this was the corner of our building, as though this is a window, okay, and then if we came over 2 feet and then dropped 16, I'm just going to draw those 2 triangles in there just lightly. That's 12, 8, 12, 8. That's where the fascia would be, right there. Okay? Without a stand. I'm not bothering with the stand right now. Well, if it's an 1812, that's going to be a little bit lower. Right? That's going to be about 10 inches lower here. And we come over, that's going to be 10 inches lower there as well. So next thing you know, we're way down here. So the fascia on the 1812 side is down here. The fascia on the 812 side is sitting up here. We can't have that. So what we actually have to do is we have to raise the wall on the 1812 on the end run by 20 inches. Right? So if this is our side wall, that stays where it is. This wall here has to be elevated by 20 inches. So basically to there. Right? So if we said that was, we're increasing the wall height there by 20 inches. So I'm going to kind of erase some of this here. I'm going to get rid of the bottom section. So we want that. We don't want that. So we basically want to hit that fascia board. Right? So if that's where the 812 fascia is going to line up, well, that's where we want the 1812 to line up as well. So if we started up here now, right, we want that angle to hit there. So that's kind of what the math is doing. We determine if we go 20 inches higher, if we come over 12 inches and then drop 18, right, we're going to hit about there. If we come over another 12 inches and drop another 18, we're going to hit exactly right at that point. So if we continue that line down, that would all line up. That's the plywood on the 1812 side, and then this is the plywood on the 812 side. They're both meeting at the same point, lining up the fascia. So that's why we did the math to the fascia, because all our math is coming to that point. Everything has to kind of line up to that. So the reason why we determine the difference in projection is because one wall has to be raised up to make sure that they meet at the same point. Okay, hopefully that kind of makes sense there. It's not the easiest thing to do on paper, but a little easier to do on a job. So basically what that means is the walls on the end run have to be either elevated by 20 inches, so either studs have to be cut 20 inches longer. We could maybe even build a knee wall on top of that, as long as this bottom wall here has a ceiling to kind of lock it, so this is not a hinge. Right? We don't want to create a hinge. So the best way is to have studs go all the way up. But maybe it's a renovation job. You could put a knee wall on top, as long as there's a ceiling here that stops that wall from curling in, because that'll be a knuckle, which could cause the building to kind of be pushed in through the wind. If it was a smaller difference, let's say we had a smaller difference here, we could also increase the stand on a rafter. Right? So if we have a rafter, we have a bird's mouth, or if it's a truss, we could raise the heel. Okay, but this here is the stand. Distance from there to there is the stand. So if our common rafter stand was 3.5 inches here, we could add 20 inches to it and make that work. That's obviously a big difference there. Not going to be practical, but if that common difference, or the drop distance here was 8 inches, it could be possible. Right? We might be able to use a 2x12 or engineered material to go with a greater stand for a common rafter. But if they're making trusses, we could just increase the stand on the truss, right? The height above the plate on the truss to make that work out. So and if we do that, so if we increase the stand or increase the heel on a truss, then we don't have to raise that wall. So it's one or the other, right? Either you raise the wall or play around with the rafter or the truss to make up that distance there, so that the fascias meet up at the same point. Okay. I know I mentioned I also wanted to talk about if we didn't know the total rise, right? So if we weren't given the end run, so if we didn't know this was 20 feet and we didn't know that was 4 feet, what would we have to do? Right, so now we know the slope. So if I just maybe make up like a new scenario there for 2 seconds. So now we know the total rise is 72, and we know the slope for that end is 1812. So let's say on your next assignment I give you the slope. You calculate the total rise based off of the side slope. How would we determine that? Kind of looking at it in reverse there, right? So we know the slope is 1812. We know the rise is 72. We're trying to find x. So again, you're just playing around with triangles there. Or we can manipulate that formula. Right? Total rise is basically run times unit rise. So what do we know? We know the unit rise and we know the total rise. So let's throw run on the other side, and then we'll go total rise divided by unit rise. So either way we could get the same answer. So 72 divided by 18 is going to basically give us an answer there. We know that that's 4 feet. Right? Just kind of working through this to show you 2 different ways. So that gives us 4 feet here. If we did similar triangles here, we have 18 over 12 is equal to 72 over x. So we're going to go basically 12 times 72 divided by 18. Right? Cross multiply. And then x will be equal to should be the same amount. Okay, it'll be in inches this time. It'll be 48. So 12 times 72 divided by 18 equals 48 inches. Why do I know it's going to be in inches? Because this is inches. So whatever I have there, that's going to be the same. So we divide that by 12. That equals 4 feet. So we're in the same ballpark there. Okay.